Welcome to the second lecture on the waves topic. In this lecture we're going to be covering simple harmonic motion, pendulums and damped and forced oscillations. This lecture is going to cover textbook sections 15.3 to 15.6. First of all, a quick recap of the most important ideas from last lecture. Simple harmonic motion is a type of periodic motion where the force is proportional to the distance from equilibrium position and directed towards the equilibrium position. So we saw that a spring, with Hooke's law, undergoes simple harmonic motion. We saw that position is equal to A cos omega t plus phi satisfies the equations for simple harmonic motion. So we can use this to describe the position of a body undergoing simple harmonic motion. Taking the derivative, we can find the velocity, and taking the second derivative, we can find the acceleration. So you can see from this line that the acceleration is equal to minus the A cos omega t is just x, so it's minus omega squared x. Okay, so the acceleration, according to Hooke's law, for a spring is minus k on mx, and for simple harmonic motion this is equal to minus omega squared x. So omega squared is equal to k on m, and so omega is equal to root k on m. Now we also showed that omega has the normal meaning of 2 pi f, which is 2 pi on t. So this gives us the relationship between the spring constant, the mass, and the period. We also saw that in simple harmonic motion energy is conserved. We showed that the total energy is equal to a half ka squared, and the kinetic energy is a half mv squared like normal, and for a spring the potential energy is a half kx squared. So this equation gives us a quick way to find the velocity of an object undergoing simple harmonic motion if we know the position and the amplitude. Okay, on to new material. We're now going to be looking at the link between simple harmonic motion and circular motion. If you imagine an object undergoing circular motion and then looking down from on top, looking at the projection of the shadow of that object, the projection is actually undergoing simple harmonic motion. We're going to prove that now. So imagine point P here. It makes an angle phi with the x-axis. This is a circle. The radius of the circle is capital A, standing for the amplitude, but it's also the radius. The x-coordinates of point P are given by A cos phi, as this is the adjacent side to this angle. The y-coordinates are given by A sin phi. Now we want to consider the case where phi is actually changing with time. So phi is our initial angle. If we want P to undergo circular motion, then it's going to travel around this circle at a constant rate, and its angle will be given by theta is equal to phi, the initial angle, plus omega t. Okay, now let's consider the speed of this particle. The particle is undergoing circular motion, so its speed, v, is given by omega r. In this case, the radius is capital A, so the speed is omega a. Now, we're just interested in the x component of this speed. You can see it's back towards the equilibrium position, so it's in the opposite direction to the position. Hence, we've got a negative sign. So the speed, here's the angle theta, this angle here's theta, this angle is 90 minus theta. So the speed is given by v sine theta, which is equal to minus omega a sine theta. And so remember, theta is just omega t plus phi. So the speed, the x component of the speed is minus omega a sine omega t plus phi, which was the same as what we had for simple harmonic motion, showing that the projection of this motion onto the x-axis is simple harmonic, at least for the velocity. Let's finally consider the acceleration. As you all know, acceleration is directed towards the center of the circle for circular motion. So the acceleration is given by v squared on r. R is a, which is omega squared a, substituting in v equals omega a. And now consider just the projection of the acceleration onto the x-axis. This angle in here is theta this time, so we have a cos theta. So the acceleration is equal in the the x component of the acceleration is equal to the total acceleration times cos theta times the negative, as it's in the negative x direction. And so we've got the acceleration in the x direction is equal to minus omega squared a cos theta, which we can write as minus omega squared a cos omega t plus phi. And this is the same as the acceleration for simple harmonic motion. So the projection of an object undergoing circular motion onto either the x or the y axis undergoes simple harmonic motion. Okay, now a pendulum. The pendulum also undergoes simple harmonic motion, at least for small angles. Let's consider all the forces acting on the pendulum. We've got the tension force acting upwards and the weight force acting downwards. So let's just draw them together as a vector diagram. Here's our tension force, here's our weight force acting downwards, and the angle between the tension force and the weight force is theta. So the angle between the tension and the resultant force is 90 degrees, as the resultant force is directed along the arc of the circle, and as the tension is the radius of the circle, they meet each other at 90 degrees. So we can see that the resultant force is equal to mg sine theta just from simple trigonometry. So we've got the resultant force is equal to mass times the acceleration. The negative here is because it's a restoring force, it's trying to move it back towards the center, and our acceleration in this case is d squared s dt squared. S we're taking as our position coordinate, it's the position along the arc of the circle. And arc length is equal to, s is equal to L theta, and so this is the s in here. So we can actually replace this s with a theta. L is not changing with time, so when we take the second derivative with time, L just remains a constant up the front. So we have d squared theta dt squared is equal to minus gl sine theta. That's replacing d squared s dt squared with d squared theta dt squared times L, and then rearranging it. Now we're assuming that theta is small. When theta is small, sine theta is approximately theta. So we can write the equation in this format. So we've got d squared theta dt squared, i.e. the acceleration of theta, the angular acceleration, is equal to minus g on L theta. Now this has the same format as our equation for simple harmonic motion. We've got the angular acceleration instead of the acceleration, and the angle instead of the position. So we can equate omega squared and g on L. When we do that, omega is equal to the square root of g on L, and then we know the relationship between period and omega. Omega is equal to 2 pi over the period, and so t is equal to 2 pi root L on g. Now you've used this equation in the pendulum laboratory exercise to work out little g. Okay, that was a simple pendulum where we had a mass on the end of a string. Other objects can also act as pendulums. If we take any object and swing it about a pivot point, which is different to its center of mass, then it will move with simple harmonic motion, and we can derive a formula to describe it. So we're going to now derive the formula to describe the period of oscillations of this object. Okay, now you know from rotation that torque is given by r cross f, where r is the vector pointing from the pivot point to the place where the force is applied, and f is the force vector. So r in this case has magnitude d, f has magnitude mg, and so this becomes dmg sine theta. This is actually directed into the board in this case. And so Newton's second law for torques tells us that the sum of all the external torques is equal to the moment of inertia times the angular acceleration. So substituting in here, we need the negative sign because this is a restoring force. It's working to get this pendulum back to its equilibrium position. We have minus dmg sine theta, that's the entire torque acting on this, is equal to I, and alpha is just the angular acceleration, which by definition is d squared theta dt squared. So we have d squared theta dt squared is equal to minus dmg theta on I. We're making the small angular approximation here and replacing sine theta with theta, and equating this to simple harmonic motion. This is equal to minus omega squared theta, telling us that omega is equal to the square root of dmg on I, and so the period is given by 2 pi root I over dmg, where d is the distance between the pivot point and the centre of mass, m is the mass of the object, and little g is just the acceleration due to gravity, and I is the moment of inertia of the object. So a question. A uniform rod of mass m and length l is pivoted about one end and oscillates in a vertical plane. Find the period of the oscillations if the period and the amplitude are small. Okay, so this rod is a uniform rod. So the center of mass is right in the middle. So the distance to the center of mass is L on 2. We have just derived the formula that the period is equal to 2 pi times the square root of I, the moment of inertia, over dmg. Now, with this rod, here it is, the center of mass here is a distance L on 2 because the rod has a length L from the pivot point. The moment of inertia of a rod pivoted about one end is given by 1/3 ml squared. Now in the exam you've been told this, unless the purpose of the question was to get you to derive it. So you do need to know how to derive the moment of inertia for some simple objects. So this is equal to 2 pi, square root of I is 1/3 ml squared. D, the distance of the center of mass from the pivot point, is given by L over 2. The mass of the rod was capital M, and G, little g, is little g. So now cancelling that out, we have 2 pi root. This L here will cancel one of those, and we end up with 2 over 3 L over G. And so that tells you the period of the rod in this question. Now we can also have pendulums or simple harmonic oscillators that work through torsion, through rotation. In this case, the torsion is given by minus kappa times theta. So this is the torsional constant times the amount of angle. So this is much like Hooke's law. F is equal to minus kx, where the torsional constant is equivalent to the spring constant k, and rather than being a linear displacement, in this case it's an angular displacement. So in this case it ends up working in very much the same way. We end up with a period which is equal to 2 pi I on kappa, and you can compare this with the normal pendulum where we've got 2 pi m on k. I is the moment of inertia, so that's equivalent to the mass, and kappa, like we said, is the torsional constant, which is equivalent to the spring constant. Okay, next we looked at damped oscillations. In reality, there's always friction or non-conservative forces acting on our objects. We've been ignoring these and saying that energy is conserved, but actually it's not. So you need to know this section qualitatively, which means that you could be asked to discuss it, to explain the relative sizes of things, to discuss the signs, or to sketch graphs describing this material, but you don't need to be able to reproduce the mathematics. Okay, so imagine a spring. When we hang a mass from a spring and let it bounce up and down, the amplitude of the bounces slowly decreases as we've got air resistance acting on it. If we were to put the spring into a beaker of water or some other viscous fluid, the amplitude would decrease much more quickly because we've got this retarding force acting on it. The mass is actually giving some of its momentum to the particles in the fluid. The retarding force is proportional to the velocity, so F is equal to minus BV, where B is some constant for a given material. So the total force acting on this mass is now the force due to Hooke's law minus Kx minus BVx. and the total force from Newton's second law is just equal to max. Okay, so this is our formula here. Now we can write this as a differential equation. Minus kx stays the same, vx is dx dt, and ax is d squared x dt squared. So this is now a second order differential equation. So you don't need to be able to solve, but if you could solve it, the solution would be of this form. X is equal to ae to the minus b on 2mt cos omega t plus phi, where this omega is equal to k on m, which is our omega naught, the natural frequency of the spring, our old omega, minus b over 2m squared. So this is effectively a new amplitude, ae to the minus b on 2m. As t increases, this exponential term is going to get smaller and smaller, and so our amplitude is going to get smaller and smaller. And this cos omega t plus phi term will make it continue to oscillate. So let's have a look at a graph of this. Here's our envelope telling us how the amplitude of the motion is decreasing. It decreases as ae to the minus b on 2mt. And then within that envelope, it's oscillating as the cos omega t plus phi. Now omega isn't changing with time, but it is different to, it's no longer equal to k on m. It's got a b on 2m function in there as well. So how would the velocity and acceleration be affected with time? Well, in exactly the same way. They would also, their amplitude would be decreasing with time, but you would continue to have these oscillations here. The velocity is going to be out of phase in this, with the position in the same way it was for normal simple harmonic motion. So we've seen that damping can make the oscillations die out over time, but if the damping's very large, then it actually stops the oscillations altogether. So the value for B for which all the oscillations stopped is called critically damped. So looking at this omega term here, and remember we've got the cos omega t term, when this term here is equal to 0, then we've got cos of 0, which is 1, which means that we don't have any oscillations in that case. So this is critically damped when this b on 2m is equal to the square root of k on m, because that's what makes this 0. So that is the frequency which will stop all oscillations. If we end up with a b larger than that, then you can see that this becomes an imaginary number and we can't actually solve it mathematically anymore. But looking at this graph, this shows you what happens when b is quite small. We get the underdamped case, which was the case we were looking at before, where it continues to oscillate but the amplitude decreases. With a critically damped case, it drops off to 0 as we only have the ae to minus b on 2m t term, and if it's overdamped, it drops off a bit more slowly. You can't tell the difference just by looking between these two. Now another thing we can do is we can add energy to the system by applying a force. If we apply this force at a certain point in each cycle, so we apply a force as a harmonic function here, F0 sine omega t, then we can be adding in as much energy each cycle as it's losing due to the damping. So eventually it will reach some equilibrium where the energy added is the same as the energy lost. Now this equation is very hard to solve. But if you were to solve it, the solution would have the form x is equal to a cos omega t plus phi, where a is equal to f0 on m omega squared minus omega naught squared plus b omega m squared, where this omega is the omega, the angular frequency that you are applying the force with. Now, resonance happens when the amplitude gets very large. There's a few ways we can make the amplitude very large. If we make omega the same as omega naught, so remember omega naught is equal to root k on m for the system, so it's like the natural frequency of the system, the frequency which the system would like to vibrate at. Well, if we make these two the same, then this whole thing's going to be 0 here, and this will be very small here, and so the amplitude is going to be very large. If we have a completely undamped case where B is 0, then this term here is 0. And if it's undamped and we apply this driving force at the correct frequency, we can get the amplitude to go off to infinity. Okay, in reality, you're not going to be able to do that, but in theory, you could. So resonance happens for small damping forces when omega is close to omega naught, the natural frequency of the system. So any system that vibrates, you can find the natural frequency of, and if you apply a driving force at that frequency, then you will end up with resonance. Okay, now a couple of questions for us to try. While driving behind a car travelling at 3 meters per second, you notice that one of the car's tyres has a small hemispherical bump on its rim, as shown in the figure. Part A, explain why the bump from your viewpoint behind the car executes simple harmonic motion. Okay, part A is relatively easy. In this case, we're just projecting the circular motion into just the vertical direction because you're only seeing the vertical part of the movement. And so when you project circular motion onto the X or the Y axis, you end up with simple harmonic motion. Part B, if the radii of the car's tyres are 0.300 meters, what is the bump's period of oscillation? Okay, so we're asked to find T for our bump. We know that T is equal to 2 pi over omega. And we're told for our car, the radius of the tyre is 0.300 meters, and the velocity is equal to 3.00 meters per second. And so we can find omega using V is equal to omega R. And so omega is equal to V over R, which is 3.00 over 0.300, and so that's equal to 10. And so substituting in here, we have T is equal to 2 pi on 10. That would be our exact answer. Or if you want to solve it on the calculator, you'd end up with 0.628 seconds. Okay, and finally, consider the physical pendulum in the figure, so it's the same figure as before. Represent its moment of inertia about an axis passing through its center of mass and parallel to the axis passing through its pivot point as ICM. Show that its period is given by 2 pi ICM plus md squared over mgd, where d is the distance between the pivot point and the center of mass. And then B, show that the period has a minimum value when d satisfies md squared is equal to I, center of mass. Okay, in this problem we have a body like this. We know its pivot point, we know its center of mass, and we know that there's a distance d between these. We know the moment of inertia I about the center of mass, and we're asked to find the period. We've derived the equation that the period is equal to 2 pi times the square root of I over mgd. This body has a mass m. Now, the problem is that this I is equal to moment of inertia about the pivot point. And all we know is the moment of inertia about the center of mass, ICM. So to deal with this, we can use what's called the parallel axis theorem. The parallel axis theorem says that I about some pivot point is equal to I about the center of mass plus the mass of the body times the distance squared between the center of mass and the pivot point. I'm going to derive this for you now. If you're not interested in the derivation, then just skip ahead a little bit. Okay, so let's think about some body. For simplification, we'll make it a flat body in the xy plane. Doesn't matter if it's three-dimensional in z. Okay, so it's the axis that we're rotating this body about. Here is our center of mass. We'll give the axis that we're rotating the body about the coordinates 0, 0, so that's our origin. And the center of mass has coordinates x, center of mass, y, center of mass. Okay, now to work out the moment of inertia, I is equal to the integral of r squared dot dm. So what we need to do is break this body down into lots of little sections. Here's one with mass dm, and add together all the contributions here. Okay, so this distance from here to here is x cm, because this is 0 and this is at x cm. Let's let this point, which we're summing over all these points, have coordinates x, y. And the distance from the centre of mass to our point, we'll call it x dash, y dash. So x dash equals distance of section with mass dm from centre of mass, and y dash is the same thing in y direction. This is in x direction. Okay, so this distance here is x dash. So we can write x, which is, this has got the coordinates x, y, is equal to x centre of mass, this part plus this part. And y is equal to y centre of mass plus y dash. Here we y centre of mass, and this is y dash here. So y, this height, is equal to the sum of these two. Okay, now our moment of inertia, we're summing up all the distance squared. So we're summing up across all these little elements dm. So we're summing x squared plus y squared. That's the distance of these elements from the pivot point times dm. Okay, now we're going to make this substitution. So we're integrating over xcm plus x dash squared plus ycm plus y dash squared. Now notice that the centre of mass is a fixed point. So xcm and ycm are fixed for the body, but x dash and y dash change because we're summing over all these points. So each of the points we sum over is going to have a different x dash, y dash. So these are functions, whereas this is a constant. Okay, now let's expand this. When we expand this, we get an xcm squared plus a ycm squared. And when we expand this part, we've got 2 xcm x dash dm plus, we've got a similar term here, 2 ycm y dash dm plus, and then each of these has an x dash y squared plus a y dash squared dm. Okay, now let's look at each of these terms. This xcm and ycm are not variables, they're fixed things. And xcm plus ycm, that's the distance of the centre of mass from our pivot point. So if we call this distance d, then this term here is just equal to d squared. Okay, so this is d squared, we can pull it out the front, put d squared, and then we've got the integral over dm, which is just our total mass m. So this is d squared m. We'll give it a capital M for the total mass. Okay, now let's look at this term. We can pull xcm once again as constant, but if we were to integrate x dash dm over all these dashes, the dashes mean the distance from the centre of mass. So to find our centre of mass, we know that there's as much mass on this side as on this side. So by definition of centre of mass, if we add up over each of the x coordinates and the increment of mass dm, this must be 0. Otherwise we haven't found our centre of mass correctly. So this term is 0. Same argument follows for this term. If we integrate over y dash dm, well, y dash is the distance of each of the increments that make up the plate from the centre of mass. So there needs to be as much mass up above it as below it, otherwise it wouldn't be the centre of mass, and so this one must be 0. Now this one, this is saying add up all these distances from the centre of mass dm. So this is giving us the moment of inertia about the center of mass. Because if we were to find the moment of inertia, we just use r squared dm, and r in this case, if we were considering the center of mass, would be the distance from the center of mass. So this is plus I cm. So what we've done there is we've proved this parallel axis theorem. What we're going to do now is go back and use it to answer our question. Okay, so we've got a clean screen now so that we can see everything. Okay, so I is equal to I about the centre of mass plus md squared. In this case, we're told that it's I about the centre of mass, and the mass, the total mass is m, and the distance between the pivot point and our centre of mass is given the symbol little d. Okay, so now all we need to do is substitute into this equation. So the period is equal to 2 pi square root of ICM plus md squared over mgd. Okay, so that's the answer to part A. In part B, we were asked to work out the relationship, or to show the relationship between I, centre of mass, and md squared for the distance at which the period is minimum. So we want d for which t is minimum. Okay, let's just show that there's going to be a minimum. If d goes to 0, you can see here this bottom term is going to go to 0 and we'll still have an ICM, so the period's going to go to infinity. If d goes to infinity, then this term's going to dominate, so we'll have an infinity squared divided by an infinity, so another infinity. So the period's going to go to infinity. So at the two extremes, we'll be going up to infinity, so there needs to be some minimum in between those. Now to find the minimum, how we do it is we differentiate. So we need to find dt, dd, and set that equal to 0. Okay, so let's do that now. So we're going to differentiate the function 2 pi. Now let's write it just to make it easier as ICM plus md squared to the 1/2 mgd to the minus 1/2. Now what we're going to have to do is use the product rule. This is a constant, so it's easy, but we'll need to differentiate each of these separately while keeping the other one constant. So let's pull 2 pi out the front, and remember this is equal to 0. So we'll start by differentiating this one. When we differentiate this one, we get a 1/2 times the derivative of this, which is 2md times ICM plus md squared. That becomes to the minus 1/2. mgd is still to the minus 1/2. Okay, now we need to differentiate this term here. So that gives us a factor of minus 1/2 times mg. And then everything else is still there. So we've got the ICM plus md squared to the 1/2 mgd, that is now to the minus 3/2. And we've got our 2 pi already out the front. Okay, now we can simplify this. This is equal to 0, so we can just get rid of that 2 pi. This 2 here will cancel, so we can write this now as md over ICM plus md squared to the 1/2 mgd to the 1/2 minus mg over 2. Now this one's on the top, ICM plus md squared to the 1/2. This one's on the bottom, mgd to the 3/2. Okay, let's get rid of this denominator. Let's multiply everything by ICM plus md squared to the 1/2 mgd to the 1/2. And on this side we've got 0, so it will be unaffected by that multiplication. So this term becomes md. This term, when we multiply this by this again, we end up with ICM plus md squared to the 1/2. And then when we multiply mgd to the 1/2 on the top, that cancels out with one of these, and so we'll end up with this to the power of 1. So we've got 2 mgd. Okay, now the mg's will cancel. Let's multiply everything through by 2d. So we've got 0 is equal to 2md squared minus ICM plus, sorry, we got rid of that 1/2 because we multiplied them together, plus md squared, and there's brackets there. This negative sign refers to both of these. So 0 is equal to md squared minus ICM, which tells us that ICM is equal to md squared, which is what we were asked to show. So that's the end of this lecture.